Basically, what I'll be going through in this talk is I'll try to introduce the very basics of side channels and mainly focusing on physical level attacks, where we are looking at power consumption and EM radiation, electromagnetic radiation from the device. And then I'll introduce what exactly do I mean by realistic and how this relates to the problem of portability. So to actually go down to the very basic, side channel is not, let's say, I wouldn't say it is something new that we have seen 20 years ago. It used to exist before. And this was actually demonstrated in, it can be demonstrated in this very simple example where you're trying to open the lock. And just by listening at the sounds of the lever, try to get to the code rather than brute forcing all the possible combination. And this is what we are currently doing on an embedded device, where we are actually measuring physical traits from a small embedded chip, computing cryptographic algorithm, and trying to recover secret key by looking at power consumption, electromagnetic radiations, or other physical parameters. So to actually just to summarize what is a side channel attack, and in a very general term, it's a non-invasive attack, which means we keep the chip still functioning. Sometimes we might remove some layers from the device, but we keep it functioning in its normal form, and then we look for the physical parameters which can leak sensitive information. It has been applied to several practical use cases. For example, the first one known was key lock, which was a keyless car opening device, and the attack was able to actually break the whole batch of the manufacturer unit. And it was also applied to FPGA bit stream encryption, and the most latest one is actually Bitcoin wallets, which were actually broken by using side channel analysis. And it's not only just secret key recovery. There could be other implications, but in this talk I'll be focusing mainly on secret key recovery. And it's a serious threat to embedded systems because there we are quite limited in cost. So we don't have sophisticated protections available to actually notch up on the device. And therefore we look at problems which are, so we actually need to strengthen our algorithm in a way so that such problems can be removed. So there are typically three kinds of side channel analysis, from a very wide perspective. One is simple side channel analysis, which is, let's say, simple visual inspection, where we look at a side channel trace and try to guess the value of the bit. Classical example is a square and multiply of an RSA, where the patterns are different, and just by looking at the trace, one can get the value of the key bit. You have non-profiled side channel analysis, which is more on the statistical side, where you apply a divide and conquer, you guess a part of the key, and then over several measurements, you try to statistically determine which key guess actually is the correct key. And finally, you have a profiled side channel attack, where you are more working in a general supervised model, where you have an access to a clone device. You try to make a profile model out of that device and use this model to actually attack your target device. So in this talk, my focus will be on the last one, that is a profiled attack, basically doing power EM attacks on embedded devices which are running cryptographic algorithms. So to look into profiled attacks, basically you start with a simple profiling phase where you have one device, and in a known key setting, you get a lot of measurements to it, feed it to a classification algorithm, and you get a profiled model. Then for the second part, which is the attack phase, you actually get your hands on a victim device where you don't know the secret key. You try to get only a few traces as fast as you can, and then you query your profile model with that to actually get the value of the secret key. And this basically, if your training phase is perfect and you have access to a large amount of traces, In the attack phase, you ideally need only one trace to break it. But because of noise, measurement noise, implemented countermeasures, and also several other factors, this one trace is a theoretical limit. Typically, you would need like from tens to hundreds or thousands of traces to actually break it. And over the years, the classification algorithms have changed. Like the first algorithm was a template attack, which is quite similar to the QDI machine learning technique. And over the years, we have seen adoption of random forest, support vector machines, and very lately, they were using deep learning algorithms. And one of the advantage of deep learning algorithm that has been highlighted in the last couple of years is that these algorithms are quite powerful in working against protected implementation, where you have some basic countermeasures. And I mean, like, if I just have to report one of the latest results, like when you compare a classical technique that is template on a protected implementation, which was reported to take 500 measurement in the attack phase, using a CNN can do it in 5 traces. So this is a power of using deep learning, but actually there is one problem in this result, and this is what is the focus of this talk. So now what we look at is basically expectation versus reality, what is expected, what we are expected to do in a profiled attack and what we actually do. So when we are talking of focusing on the attack phase where you are querying an unknown or a victim device, you are actually, you have a different device where you cannot normally profile. But what most of the work which have been reported in this recent time, they are actually looking at a different set, which is they're taking the testing set from the same device. So this obviously introduces a bias into your analysis, and this can actually lead to pessimistic security evaluation. So in the following, actually, we conduct a set of experiments to show how this bias is, and on a very simple implementation, to what extent can this actually offset your security evaluation. So to put this problem into a simple definition, so we look at the problem of portability, where you have two devices, B and B dash, which are exact copies of each other, and but there are some uncontrolled variation between them. And how can we actually train on a clone device B dash to actually mount an attack on B? This is the problem that we'll focus in the next slides. And to actually do that, we did some studies. So we started with 4 copies of the same device. It is an Atmega 8328P microcontroller, which is an 8-bit architecture, very simple. And this is actually used to report most of the deep learning research in the past 4 or 5 years in power and EM side channel analysis. So we took this architecture, and we queried this board with different keys. And the idea was to actually create 4 different scenarios. One is same device, same key, and going towards from same device, different key, different device, same key, as well as different device, different key. So going from the best case to the worst case. And to actually accelerate, we have some parallel measurements so that we can get a lot of data sets from that one. And if you look at these, like the whole measurement setup, you have several sources of uncontrolled variation. First of all, your chip has some process variation. You have discrete components on the board which has variation. You are connecting it through different wires to the oscilloscope, which has like a set of process variation, as well as the oscilloscope component itself. And when they are placed in a different part of the room, there will be minor environmental variations, and all these coupled together can actually have an effect on your measurements. And basically, if we just take a very rough look on the signal quality, you can see that when we are comparing, so on the right you have cases which are same device, same key, which is the best case. You have like almost negligible differences, and on the other side where you map all the data set together, you can see that the signal quality varies from point to point for different measurements, although they are running the same algorithm under the same conditions. So to give you like this snapshot of a result, so this is the result when we are actually attacking these data sets using MLPs, that is a multi-layer perceptron. And basically along the x-axis, it plots the number of traces that you need to query to get the key, and on the y-axis it is the rank of the key. So typically when it converges to 0, you have found the good key, which means the attack is successful. And you can see like the worst case, which is different device and different key, is actually at least 20 times worse than the best case. And this exactly is the problem of portability, or what is ignored in most of the publications. And this is something which we actually try to highlight in this paper. Now, when you compare 2 traces to 20 or 200 traces, that might not look that bad, because I mean in terms of measurement, these are only a couple of seconds more. But when we are talking about protected implementations on more recent computer architectures where you have a very low SNR, this problem can actually be much worse. So you are looking at from traces varying from a couple of 100,000 to million, and like when you are considering a security evaluation where you only have 1 week to actually look into side channel problems, these kind of differences can be quite worse. So to look the whole picture all together, we have in general all the sets. So here you can see like starting from 2 traces to break the attack, we are in the worst case where like the best algorithm can break in 30, but for a simple algorithm like naive Bayes or random forest, even with 100 traces, we are unable to break it. So overall, what we observe here is around 20 times degradation from the best case to the worst case, and like depending on the algorithm, this can actually be quite worse. And the reason why this happens is when we investigated and we looked at the accuracy of the training versus validation on the same and a different device, we can clearly see that this is an overfitting problem. And what's actually happening is when we are trying to present traces from a single device, the machine learning algorithm actually tries to learn the whole parameters, including the specific parameters of that device, and which actually creates problem when we apply the same model to another device, and therefore deteriorates the result in the process. So to actually overcome this process variation problem, like our straightforward solution was actually to have a multi-device model where we can learn from different devices. Although our testing device still remains a distinct one, but we should look at different samples so that when we are training, we could also capture these variations between different devices and actually make a more robust training of our model, which can actually help us. So again, coming back to the definition now, instead of looking at one device B dash, we are training our model on a set of devices between B0 dash to Bn minus 1 dash to actually create a model to attack the actual device, which is B. And actually, when we perform the testing using this, we see at least up to 10 times improvements in this case. Finally, we actually apply this technique to actually one of the problems that is quite common in actually sidechain analysis is electromagnetic sidechain analysis. So EM is preferred over power in several cases, and the reason is, first of all, it's very easy to use because you can just put the probe near the device at a particular position, and you can at least start to measure. Of course, you'll have to do a trial and error to find the position, but it is much simpler than modifying the board architecture and as well as rerouting some parts of the PCB. You can have high SNR and you can capture like really local information. But the thing is, if you have to do a realistic profile sidechain attack where you'll measure on two different devices using the same probe, there will always be a small error in the placement of the probe. Even if you use like a motorized XYZ controller where you are placing the chip and the device automatically, there is always a slight disturbance in the position. It could be in the distance, orientation, and that again is a problem of portability. And actually, when we look at this problem and we try to apply the MDM model that was previously proposed, we actually see that when you learn on multiple EM placement on the same device, you can actually try to attack it much easily. And so therefore, coming to the conclusion, portability is an issue when we are looking at profiled attacks, especially with machine learning techniques, and therefore we should take that into the account. Otherwise, the evaluation that we are doing or the security certification we are doing can be misleading. To overcome, we proposed a MDM model which has a direct application to even to EM measurements. And in future, what we are looking at is to see if we can apply these techniques to heterogeneous devices where the devices are not the exact copy of each other, but has like a different family. For example, trying to apply from one generation of device to another, or and also trying to extend the MDM model in a case where multiple devices are not available, but can we bag on models or simulation models that are available from the manufacturer about noise variation or process variation, and can we plug it into the system to generate the MDM model? Thank you, and okay. I'll be happy to take any questions.
Okay, thank you. I'll ask a clarification question. So when you mentioned these 4 situations, right? So same device, different keys. My understanding here is even when you do training on one device, you have to use different keys already. So right, you are not doing training on just one key on that device, right? Or do you?
No, actually, there are different variants of the attack. So in some cases, you can actually attack with the same key. For example, in one of the introduction example I was giving, where you have the same key for the whole manufactured batch, like training with one key can actually already help you.
Right, but if you are trying to learn the secret key in the device, you have to look at the, whether there is a differential behavior when there are different keys. So that's how you are going to learn the key, right? I just don't understand how you can, tell the secret by just learning the behavior using just one key.
So in this case, you don't actually directly work on the value of the key, but you look at a key-dependent value, and this will change every time you change the plain text. So as long as you can profile that key-dependent value and the plain text, you can actually roll back. So,
but if you have just one key, that key-dependent value would not change either, right?
No, but as soon as you change the plain text, that key-dependent value will keep changing.
Okay, maybe I'll take it offline. Thank you.
Sure.
I have a quick question about using guessing entropy for your security evaluation. Yeah. Have you tried other entropies like mean entropy, minimal guess entropy? Is this depends on that measure or?
No, actually, so we took guessing entropy because that is like the widely accepted metric in this area, and also basically these results are it's kind of mean because we are repeating the attack several times and then looking at the trend. Basically that.
So the other measure, I guess they were worried about worst case scenario,
yes, exactly.
If you can obtain.
Okay, I think that's all. Enjoy your lunch. Okay.
Thank you.